2016, the security firm CrowdStrike concluded that the headquarters of the Democratic National Committee had been breached by a threat actor named Fancy Bear. Fancy Bear corresponded to the Russian Military Intelligence Directorate, or GRU. As part of their operation, Fancy Bear managed to steal thousands of emails from DNC servers. These stolen communications were then given to WikiLeaks for surfacing as part of a propaganda campaign to exert influence over the 2016 election. According to the NSA and the FBI, the malware used by Fancy Bear in its operations was named DrovoRube, which included a specialized backdoor developed by the GRU's Cyber Warfare Division. According to CSO Online, 80% of all security incidents are the result of phishing attacks. Also from the published study, 94% of malware is delivered via email. However you wish to analyze and distribute the numbers, it's all but conclusive that one of the most popular vectors of entry for threat actors in the cyber domain is through malware, usually distributed through creative variations of social engineering. In this video, I'll provide a brief demonstration of some of the data exchange that occurs at the data packet level when malware is attacking a system. By analyzing the network data packets, we can get a better understanding of how a particular piece of malware operates so we might recognize it later in network traffic. My name is Dr. Jonathan Adkins. I have a PhD in Information Assurance and a Master of Science in Digital Forensics. My areas of personal interest and research are network penetration testing, malware analysis, evidence recovery, and machine learning algorithms. The use of artificial intelligence in cybersecurity is still in its infancy, and it will only grow in the future. I mentioned the DrovoRube malware in the introductory slide. I'd like to elaborate on this for a moment, as this is the perfect segue into the focal point of my presentation. DrovoRube is an example of a backdoor, or an advanced persistent threat, or APT. Its purpose is to provide an external threat actor with a command and control access to an organization's network resources. At its essence, an APT comes with three basic items of functionality. These are the ability to traverse a directory structure and explore its contents, the ability to upload files, and the ability to download files. More sophisticated APTs will have additional tools such as a screen capture function, a webcam pirating option, a keystroke logger, and other functions. DrovoRube, like many other APTs, consists of a server-client architecture. The server is the component which provides an attacker with command and control capability. The client component is deployed to a victim machine. In the case of DrovoRube, the connection that was established between a victim and attacker was created using something called a TCP socket. This is programmer language jargon for a network connection object that is created using a language such as Python. TCP, or Transfer Control Protocol, is one of two primary types of connections. TCP is slower but more reliable with regards to maintaining a connection. Another connection type, User Datagram Protocol, or UDP, is faster but not as reliable as TCP. YouTube makes use of UDP in part of its operational model. Netflix and Amazon Video use TCP. The rest of this video will be divided into two parts. In the first part, I'm going to discuss some Python code that's part of an APT server. In the second part, I'll execute a screen capture command from an APT that I created using Python in a controlled environment. All of the data packets associated with the APT's screen capture command will be collected by Wireshark. I'll then discuss some forensic information that can be found in the data packets. See you in section 1. What you're seeing on your screen right now is my Kali Linux environment, which is running on VirtualBox. In the Kali Linux environment, I have my Python IDE of choice, which is PyCharm, currently up and running. The multicolored text that you see is Python code. If you look at the current active tab on the upper right of the PyCharm IDE, you'll see that the Python script that's active is the server portion of an APT that I've created. The client component of the APT is running on my Windows 10 machine, which is serving as my victim. Both the Kali Linux environment and the Windows 10 machines have different IP addresses. They both reside on the same 192.168 network. There are two blocks of code that I'd like to highlight in this section, as they'll add further clarity and context to the data packets that we'll be examining in the next section. The first block of code that I would like to discuss can be seen in lines 81 and 82. Line 81 identifies a user-defined network connection, which in coding parlance is called a socket. I'm not going to go into any great detail on this right now, as I'm planning on doing a series of videos on creating and deploying an APT where I'll address all of these concerns and topics. What I wish to draw your attention to in this current discussion is the second parameter of the socket function in line 81. The code, which reads socket.sockstream, indicates that our socket will have a TCP connection. A TCP connection will be more reliable to maintain constant connectivity with a victim machine. The second items of Python code that I'd like to discuss can be seen in lines 12 and 18 of the PyCharm editor. In these two lines, you'll notice two functions. These are dump_s and load_s. These two functions provide a service for us called serialization. What serialization does for us is break objects down into chunks of data which can be sent back and forth across a network connection. To extrapolate further, this will allow us to upload and download files from a victim machine. So how does this help us out forensically speaking? It means that data being uploaded and downloaded, such as stolen files or screen captures of a desktop, will be stored in serialized chunks in TCP data packets. In the next section, I'm going to send a screen capture command to my infected victim Windows 10 machine. I'll be capturing data packets with Wireshark while I'm doing this. In the final section, we'll discuss the data packets that were collected after the screen capture command was sent. See you in the next section. Welcome back. In this section, I'm going to execute a screenshot command from my APT server component while I have Wireshark running in the background collecting network data packets. We'll be analyzing these packets in the section that follows this. My APT is actively connected to my Windows 10 victim machine. You can tell the APT has connectivity due to the reverse shell prompt that's displayed in the terminal window. The shell prompt displays the IP address of my victim along with the port number on my Kali Linux system that's accepting the connection. I referred to this as a reverse shell because the client component of the APT makes a connection back to the attacker machine after the client component is executed on the victim's computer. I have the screenshot command already typed into the reverse shell prompt. Once I enter this command, it will be sent to the Windows 10 victim and the data packets will be collected by Wireshark. I'm only interested in the packets that are associated with the screenshot command, so I'll break the APT connection right after the command is sent. Then I'll see you in the last section to discuss the data packets. As I mentioned at the beginning of this video, the focus of this presentation is to demonstrate and discuss some network forensic information that is generated as a byproduct of malware activity. I'll discuss design, functionality, and deployment of malware in a later series. Now, what you're seeing on your screen is the network data packet capture of my APT malware when it executed a screenshot command on a victim computer. As you can see, there are TCP and UDP packets. We are only interested in the TCP packets, so the UDP packets are superfluous. You might not see it in the top menu bar, but the text TCP is entered. When this filter is executed, Wireshark will display only the TCP packets from the PCAP file. The first thing that you'll notice is that there are two IP addresses in the stream conversation. My Kali Linux attacker machine is the address that ends in 1.180. The victim machine ends in 1.3. There are three items that I'd like to point out with regards to this PCAP file. If we look at the very first packet in the list, there's something readable in clear text in the hexadecimal of the payload information. At the very bottom in clear text, you'll notice that it says screenshot. This was the command that I sent from the attacker machine. If we move to the third packet in our filtered PCAP file, we'll observe another interesting piece of information. In the payload section of the packet, the data is in raw format, so we see it in hexadecimal. To the right of the hexadecimal data, we see the letters and characters in clear text. At the very top of this column of characters in clear text, we see the letters P, N, and G. If we look in the first row of hex data, the first 54 hexadecimal characters serve as a preamble for the data that follows. Following the preamble, there are 4 bytes that we should note. These are 89, 50, 4E, and 47. These are 4 hexadecimal bytes that correspond to the letters PNG in the columns of clear text to the immediate right. These bytes are in digital forensics are what are known as magic numbers. Magic numbers are digital signatures that appear at the head of files to indicate what kind of file they are. These signatures let the file system know what kind of application is needed to open the file. Since the digital signature in this case is an image of file type PNG, the file system will call the default image viewer to open it. Everything past the digital signature is image data that we as humans will not be able to interpret without the use of an image viewer. I had mentioned in a previous section where we reviewed Python code that we used JSON serialization to break the screenshot into chunks that could be uploaded and downloaded over a network connection. I wanted to point out one last interesting piece of information. If you look at all the packets whose destination IP address is 1.180, all have payloads that are rather large in size, as we can see by the numbers in the length column. Taken individually, these payloads are nothing but unreadable chunks of gibberish. However, if all the hex data from these individual chunks were reassembled together in a single file, you would have the original screenshot.png file. So, if we were to extrapolate on what we are seeing here to network forensic analysis in general, there are 3 things that you can keep stored in your analyst tool belt with regards to malware. The first is that Transfer Control Protocol, or TCP, is a popular method by which threat actors seek to achieve and maintain connectivity with victims. With this in mind, TCP packets often contain the valuable information we seek as investigators. A second thing to keep in mind is that some clues attributable to an attack can be found in clear text in the payload data. There might not be as much readable data as we would like because it's often encrypted or in binary format. Still, you may be able to capture things like commands sent in clear text from the attacker machine or some file signatures. The last thing to consider is that when a conversation is isolated in a PCAP file, it's also possible to extract data that has been transferred back and forth between victim and attacker machines. The sizes of the payload data in packets should be examined. If a digital file signature is identified, it's possible to reassemble the file to its original form by extracting the disparate hexadecimal contents of the packet payload data. I'll be back soon with a series on how to construct and deploy an APT. Until then, see you soon, and happy hunting.